Hello, konnichiwa. I'm Matthew Kear, and together with Ferruccio Vicari, we're going to give an update on the autonomous autorotation flight mode. Ferruccio, do you want to say hi?
Hi, everybody. Good morning.
So, what are we going to cover? As already identified, Trad Heli is not the most widely used firmware within the ArduPilot ecosystem, so many people may not be aware of what an autorotation is. So I'm going to give a quick overview and explain what it is. We've in the flight mode itself, we've broken down flight phases. We've broken down the flight phases into a number of partitions. So we're going to explain what that is and go through that. Then we've got a few different controller definitions. So we're going to explain where they're used and what they do. Then Ferruccio is going to take over and talk about the flare phase, the decision logic behind that, and how do we smoothly land the vehicle down on the ground. And he's also got some excellent real-life demo videos that he's going to talk to as well. Then we're going to round out with just talking about some future work we've got planned. Okay, so autorotation, what is it? In a nutshell, it's the helicopter's equivalent of a glide. It's whereby we can shut off the main engine and we can still maintain safe flight, but we are gliding towards the ground. Typically, its sort of main use case is an emergency maneuver because it's an engine out case, but obviously there's a lot of fun practice cases as well. So just to compare and contrast, I've got a force velocity diagram showing down the edge of a rotor blade cross section, and you can see, hopefully this will show up, this main black force arrow here, torque, which is being supplied by the main rotor or the main engine. That gives us our large lift vector and our large thrust vector as a result that enables us to maintain flight. In the autorotation case, one of the two different things here is that we've got a significant descent velocity component, and then we're managing the blade collective angle, so the pitch of the blade, such that we can manipulate our lift vector so that it's facing forward. The in-plane component of the lift vector is then what drives the main rotor around, and that's what enables us to have or maintain safe flight. Okay. So as part of the autonomous flight mode, or the assisted autorotation flight mode, we've broken the flight down into a few categories. So I'm going to go through those and what we're trying to achieve in each part. So the entry phase, usually this will be, well, it can be initiated because we've had an engine failure. Cough, cough, splutter, splutter, our engine has failed. The first thing we need to do is adopt a suitable collective position such that we can maintain our head speed. Now that's a little tricky because we've gone from driving airflow down through our rotor to having the airflow now having to come up through the rotor to push it round. So aerodynamically, it's a mess. So there's a very tricky thing to do to try to survive through that condition. Then the other part is we either need to build or maintain forward airspeed to build energy within the vehicle as we're managing it to go down. So once we've entered into the auto-rotation, then we just have to sustain that flight down towards the ground. So we're maintaining our head speed and we are either continuing to build or maintaining our forward airspeed. It's during the glide phase, if we have enough height, that we have the opportunity to do a bit of navigation, either to turn into wind or to try and find a better area with which to land. Then, as we approach the ground, this is the point that we want to start to arrest the descent. This is done by pitching the aircraft up, effectively changing the incidence angle on the main rotor disc, and increasing the lift that's available to the vehicle so that we reduce our descent rate. And we're still trying to manage that head speed so that we don't end up in an overspeed condition. That as we start to reduce that forward airspeed, the final part is the touchdown. And this is where we now sort of switch our flight regime again. And we are using what energy we have left in the head. So the inertia of the blades is still going to keep the rotor head driving around to a certain extent. And we're then going to use the collective a lot more like normal helicopter flight to soften the landing, controlling our descent speed. I've already mentioned that there are a few different controllers. So there's an overview, or an overlay, I should say, of the controllers that we've got and where they're enacting. So speed control, that's in forward and lateral speed. That's active throughout all four of the phases shown there. The head speed controller, whereby we're using collective to maintain head speed, is in the entry, glide, and flare. And then at the last part, we're flipping over to the touchdown controller, whereby we're using collective and whatever energy is left in the head to then soften the landing. So sometimes this can all be a little bit abstract. So I've got some results from the work we've done in real flight. So I'm just going to go through a couple of different cases, and that'll hopefully give everybody a bit more context as to exactly what this maneuver is. So from the first video, I apologize over Zoom, it might be a little chunky. Yeah, in the first video, we're going to be entering from very high, 330 meters.
Entry. Glide.
Now the vehicle is in the glide, and have an option to start doing navigation. Pilot can use the door stick, and the controllers probably coordinate controls and navigate flying. As we approach the ground, we're constantly evaluating whether we're going to flare into the landing.
Flare. Touchdown. Landed.
There's a little bit of a spoiler for Pete Hall's talk later. You can see I've got a custom telemetry dashboard up on the left there. So he'll talk more to that later. Okay, so from the remote pilot's point of view then, just for you to see the aircraft coming down onto the ground, this is the same condition. Aircraft is currently on the glide.
Flare. Touchdown. Landed.
Okay, so that was initiated from very high countries up to about 120 meters. So let's look at a case whereby we haven't got quite as much height available to us. So now we're going to enter with some forward airspeed to 120 meters above.
Entry. Glide. Flare. Touchdown. Landed.
As you can see, practically, we don't have much time for maneuver. I would also add, in comparison to some of the real world testing that I've seen, the glide ratio we seem to get out of the sim is a little bit aggressive. So in real life, and it very much depends on your rotor loading and how much mass you've got, but we have a little bit more time for navigating than that. And then another even more realistic case, flying at 40 meters, 14 meters per second.
Entry. Flare. Touchdown. Landed.
It all happens very quickly. You'll notice that we touched touchdown with forward airspeed there, and that's partly because within the autorotation flight mode, to prevent tail strikes, we have to constrain the pitch back limit as we get close to the ground. We gently bring that in. The consequence of that is, of course, that we might end up touching down with forward airspeed. So we cannot do everything. And this is a very well-established problem within manned helicopters. And I know Ferruccio's got a diagram, the velocity height diagram, that you can talk to later about that. So finally, the last thing I want to talk about is Switching off your engine and going into the flight mode is a somewhat bold thing to do when you've got a perfectly functioning aircraft. So we've also got the bailout case, whereby once we've entered into and are gliding, as part of the practice and the tuning of the controllers, we can also exit back into a powered state. So this is just a demonstration of that.
Autorotate. Entry. Glide. Bailout. Alt-hold.
And so that was an example of exiting the flight mode, re-engaging the interlock, and exiting into alt-hold, resuming powered flight. Okay, so hopefully that gives you a good feeling for what we're trying to do with the assisted auto-rotation flight mode. Come on. Okay, so moving on to some of the controllers. First of all, talk to the head speed controller. As already mentioned, we're using collective to control the head speed, and we have a closed feedback loop on head speed, i.e. RPM. Typically, what's quite commonly used is little Hall effect sensors and a magnet in one of the rotating parts of the structure. So we're using AP-RPM to measure the main rotor head, and the controller itself is actually just a P controller with what we call a following trim. The following trim is where it's just this low pass filter on the collective control. This is in many ways a lot like a PI controller. The main thing that doing it via a filter instead of an I term gives is that we have, it's the APIs make it a little bit easier to then change the cutoff low pass frequency without seeing steps in the controller versus if we're changing the gain. It's just possible, you can do either. So whilst this works, there are still significant errors in head speed. So the plot that's been shown on screen now is the measured head speed error as a percentage to the target. And this is a real flight that was done, and we've seen sort of up to 25% in the main rotor speed error. With helis, because our rate tune and our attitude tune, therefore, is a function of our head speed, much error, we end up not having as tighter tune on our attitude control. This needs to improve. So it works, it's safe enough at this scale. It's definitely an area of improvement. I'm looking at the potential opportunities of some model-based control, but haven't had a chance to do any work in that area yet. Okay, speed controller, and by that I mean forward speed. What's quite important in this application is that it's defined in the body frame. You've seen how high the descent rate is of the vehicle, and the descent rate in earth frame contributes a significant part to the forward speed of the aircraft in body frame. So we have two inputs to this controller. The first is the pilot directional input. So at the moment that comes in on the yaw stick. And the second is the forward speed set point. Now, in the entry and glide, that set point is just a single value set by a parameter. I want to fly at 11 meters per second, for example. In the flare and touchdown phases, we're smoothly moving that speed set point to get the vehicle to maneuver through that pitch up maneuver. The forward path to start with, the first thing we do is we apply an Excel constraint. So there's a parameter within the auto-rotation flight mode, and that's simply applying some input shaping onto the forward speed set point. So we don't get a big step, bang, I want to go straight to my target. We're smoothly increasing the target from our end condition. Then that feeds into what is simply an ACPID object. We're deliberately trying to use what's already there within the code. We don't want to reinvent the wheel. And that is a ID controller that's closing the loop on the measured forward speed. The output of that gives us an Excel target. So now I'll just talk a little bit to the other part of that, the lateral side. So the pilot's directional input, it's a value between -1 and 1, and we need to convert that into a lateral acceleration target. So we just multiply it by half of the accel max. Again, this is the accel max within the flight mode, the autorotation flight mode param set. And the reason for the half scaling is because we never want to allow the pilot to over-index or drive the helicopter to try and turn direction too much. We always want to prioritize building forward airspeed. So that's why that 1/2 weighting is there. So the output of the directional control, it gives us the lateral acceleration target, and the forward speed control gives us the forward accel target. So they are then applied in a circular constraint on the accel limit. And if we do hit that limit, we are then stopping and preventing the I-term wind up. With our accel target or limited accel target, we can then calculate roll and pitch angle. And then that roll and pitch angle is then compared to the angle max. And this is the angle max of the vehicle that everyone who flies copters is familiar with. Again, if we hit that limit, we are preventing I-term wind up. And finally, to complete the full control, we need to calculate a yaw rate. So we take the forward speed target and the lateral accel target, divide the velocity by yaw rate in radians per second, and unit conversion into centimeters degrees per second. We can then pass that all into the attitude control. So in that block diagram, there are a few blocks that are missed out on the end as to what's going on in the attitude control and the actual plan to the vehicle. But the end output that we then measure is the forward speed to close the loop. Okay, so I'm going to stop talking and hand over to Ferruccio.
So about the flare phase and touchdown phase, what the code does when we enter the flight mode is to determine where the helicopter is in terms of total energy, so altitude above ground and forward speed. At this point, it's very important to remember the deadman curve or height velocity diagram, like in this slide. And this basically tells us which direction we have to take. If we have enough altitude, we can enter dynamic flight conditions, so increase forward speed. Or if we are at very low altitude, we need to switch at hover autorotation case. So initially, the code does some calculation to estimate what the ideal flare altitude could be. And based on that and on the actual translational velocity of the aircraft, it will decide if either going to steady state glide or switch to hover autorotation. In the case of entering the steady state glide condition, the helicopter will accelerate to the desired forward speed, and upon meeting certain conditions, it will recalculate and update the flare altitude. So to decide to have a better estimation of the ideal flare altitude. And then, as a last step of the logic, the state machine will switch into touchdown for preparing for landing. We can move on. Matt? Thank you. So what is the flare phase? Basically, we want to convert the translational and vertical energy of the helicopter into a smooth braking condition, let's say. So what the pilot normally does is to lift the nose of the helicopter and basically trade off all of the almost all of the forward speed into a decreased sink rate. What we are using here as a basic idea for the whole calculation is to estimate the relative wind that goes into the rotor, especially looking at the component orthogonal to the rotor disc. And as we can see, this component is primarily responsible of increasing the momentary increase in the rotor thrust, and thus creating a deceleration factor into both the forward speed and the sink rate. As normally happens, this condition tends to soften the sink rate and come back to a new, let's say, to a new steady state condition, which is when we detect the flare complete case. So basically, as on gyrocopters, we use forward speed to decrease or increase the sink rate. There is a conversion between as I said, the forward speed and the sink rate, and this is managed through the pitch up of or pitch up attitude of the main rotor. When we have reached the final condition in which there is basically no possibility of breaking any further the vertical descent, we are ready to switch to the touchdown phase, so level the attitude and cushion the landing. We can move to the next one. So for the calculation of the altitude at which we perform the flare, I've used the first Euler law and some integration to get to this big monster we can see here, and a rough estimate of what the altitude could be. Of course, this model doesn't take into account any higher vehicle dynamics, like it's not modeled how fast the helicopter will pitch up during the flare maneuver. So basically, we consider the contribution of three main terms into the equation, which is the pitch up phase. Basically, it's estimated using the input TC from the altitude control to get an idea of how much time we will spend to reach the target angle on the pitch axis. And then we add the calculated flare distance. And finally, we consider the time for touching down, which is basically calculated through through a parameter set by the user, which defines how much time window we have to perform the touchdown. Okay, the next one. So as I said before, the code needs to run some estimation before outputting a flare altitude value. And this is due to the nature of the previous equation. We need to know the actual weight of the helicopter. So by running some basic blade element derivation formulas, we can estimate both the thrust of the helicopter at over and the rate of descent estimated, and of course the coefficient of drag. The basic idea is to consider the rotor disc as a leaky plate, we could call it that way, and estimate the braking action that the rotor does when it comes into a vertical descent, let's say. So the code retrieves some values from copter, like the hover collective position, and converts into a blade angle of attack, and the nominal rotor speed, of course, and some used parameters which are needed to characterize the rotor. So the rotor solidity, the diameter, and the lift slope of the airfoil. This method has some limitations. Of course, it's a 60 years old technology, so we can consider the rotor blades as non-twisted and with a rectangular planform view. And at the minute, we are not considering the tip effects of the rotor blade. Okay. So here is a little bit in-depth view of what the model does. So on this graph, we can see the sink rate, so the vertical speed of the aircraft while gliding. And we can see in the yellow range, let's say, where the flare happens, it's actually where we convert the forward speed to smoothen the vertical speed. And we can see the model for the vertical velocity and with the red dotted line, and the data retrieved from a test flight with the blue line. We can see that the contribution of the flare to decreasing the actual vertical speed is not that large. Indeed, the biggest part of the job is done during touchdown and completely managing the descent using the collective. This means that the model can effectively and safely calculate the altitude needed to perform the flare, but to make it successful, it depends literally on the energy stored in the blades, because that's what's left for completing a successful touchdown. Okay. About the flare calculation, well, the initial calculation is based on some rough estimations which derive from vertical autorotation and desired forward speed. What happens is that once we reach a steady state glide, we run again the flare altitude calculation with current sink rate and forward speed. So we update the model with a better and more accurate calculation of the drag coefficient of the rotor disc. And this can only happen if the condition of the glide are steady. That means that in this case, after some research, we are monitoring the sink rate and comparing it to the low pass filtered value of the sink rate. This because it can happen that during the descent, due to wind or due to some other factors, the sink rate and rotor RPM can be not very stable. Of course, we want the calculation to be performed in a steady state condition in order to be accurate. So there is some logic behind to make it a safe assumption about the timing of when to perform this calculation. In this case, as I said, we look at the sink rate and having achieved at least 80% of the desired forward speed. Okay, Matt? So for the pitch axis control during the flare, as Matt explained, we are using the forward speed controller, and we can see during the flare phase there is a sudden heavy pitch up, which by default is limited to 20 degrees. This for a number of reasons. Of course, the tail boom interference with the ground could become a problem if we don't perform a level out condition quick enough. And as a general experience, I've found out that 20 degrees is plenty has plenty of headroom to performing a successful flare action. Outside of this, there is the pitch of the forward velocity controller. There is an external controller that basically monitors when the flare can be considered completed. And the monitor works basically looking at the forward speed. So we need to have dropped a little bit of speed, and we look at the vertical acceleration. That means that we want to see when the flaring action has completed. So all the energy has been transferred effectively. This because if the flare is too early and we kept the pitch up attitude, we would see a sudden increase in the sink rate. So after reaching a steady, the minimum, basically the minimum of the sink rate, if we would keep the pitch up, we would probably still decelerate the forward velocity, but sink rate would start increasing again, so make it even then more dangerous for the subsequent touchdown phase. So this controller works outside of the forward speed controller and just monitors, it's just a safety monitor to level out in case the flare is completed. Okay, next one. So the touchdown controller is responsible of, after having performed a successful flare, is responsible to reduce the vertical speed down to the minimum possible, which in this case, it's generally accepted as around 150 to 300 feet per minute as a vertical speed. It's a simple P controller with a feedback on with a linear pass filter of the collective value, which has which works as a following trim, and it basically the set point is the sync rate desired, which is linearly moved to zero using linear interpolation with the ground proximity. The touchdown controller has a little extra safety feature, which kind of tries to make the height velocity diagram a little bit more flexible for radio control helicopters. That means that it could happen to enter a hover autorotation and we are slightly above the maximum hover altitude for performing a successful autorotation. So if this happens, basically the logic looks at lowering the collective momentarily until we reach the right altitude above the ground to start increasing again the collective and cushioning the landing. This does not mean that it is safe to perform such a maneuver from hover altitude above, let's say, the rotor diameter as a reference, but it could save a lot of energy in the rotor by decreasing the blade angle of attack, basically. So it's a stretch to the height velocity diagram. Okay, next one.
Want these in, Ferruccio?
Yep. Yeah.
Okay, so these are some real-world results that from Ferruccio's testing. The helicopter is quite high at the moment and will come into view. It's just at the top of the frame at the moment. These videos will be a lot easier to see in the YouTube recordings after, so I do encourage you to go and have a look at some of these. This one on the side is Ferruccio testing the hover autorotation case.
Landing complete. Auto rotate flight mode. Motors no terrain data. Auto rotate flight mode.
So there is a small dot appearing in the sky now. You should start to see it in the middle of the screen.
No terrain data. No terrain data.
Nice. Oh, right. So that's kind of an overview of all the things that we have done, but there's still a lot more that we want to do. I've already alluded to it, and often when we talk about it, we call it the assisted autorotation mode, and that's because there are a number of steps that we need to take to make it autonomous. One of those is actually the power failure detection and then automatically switching to the flight mode, just like we would with the battery failsafe, for example. I know Ferruccio has done some work in that area already, so we're going to be looking to expand on that and bring that in. Then something that I'm working on is very conscious that for this to work reliably, we have a heavy dependency on the measurement of our head speed. So I want to build in some redundancy there by adding a median RPM instance to the AP-RPM library. In a vein, we need an accurate measurement of the vehicle's height above the ground. And part of that is bringing in redundant LiDAR, which we already have to a certain extent, but also direction LiDAR by using median weighting. So some of you may remember that I broke out Copter's surface distance code into its own library, AP surface distance, and that was pre-work bringing this in. And summarizing. So we give you an overview of the auto-rotation flight mode. We've explained the controllers that we've used thus far. Ferruccio has taken you through the flare phase decision logic and explained some of the math behind that. We have a couple of open PRs to get everything that was discussed merged, so it will be available to play with soon. Though we have many more improvements to be added. So thank you very much. Arigato gozaimasu. And I welcome any questions.
Excellent, Matt. It's not clear to me why we need forward velocity during the glide phase. Does this have something to do with a maximum negative collective angle?
Good question. So effectively, it's all about managing your energy state toward the ground. And certainly what was born out of manned aviation, and we get away with a little bit to this extent, is we cannot overspeed our head just because of stresses on the head. We also have the dependency of like our rate control tune and things like that. So we need to keep our main rotor speed the same. So the other way to build energy is to build forward speed. We build that forward speed, then effectively our flare phase becomes exactly like we flare with a plane. And that's the main motivation. So something that was shown, if I going back real quick, Ferruccio was talking to with the speed height diagram. So this is something that's very familiar to those that are familiar with helicopters. So this red curve here is often called the dead man curve. And this is basically a representation of the flight envelope for helicopters, whereby helicopters should ideally fly faster when closer to the ground, because we cannot safely auto-rotate if we're inside this red curve. And that's all around knowing the capability of the vehicle and being able to manage the energy state for safe landing in an engine out failure case.
Is there a maximum amount of time for a system or pilot to detect and enter auto rotation, or is it just as long as you have energy?
Yes, there is a maximum, definitely. And this is the key part why we need to automate this. Currently, let's say, take for example, we're flying in alt hold or any position controlled mode. The natural response in a power out failure for RG-Pilot would be to try and maintain the vehicle's height. To do that, it will then raise the collective, increasing the drag and slowing the rotor. So the natural response is that it's going to rapidly slow the head. So that time window is quite short. So in the practical sense, that time window is short for the remote pilot to detect the failure and switch into it. This is why we're working on the automated detection piece.
I don't have much experience with helicopters. Sorry if this is a naive question, but in the case of this, a main rotor failure, and you're going down, you'd still need yaw control, right? You'd still need some form of yaw control. And so if there's like a complete, I don't know, motor failure, this would be harder to do. Is that correct?
So strictly speaking, you don't really need yaw control because you no longer have torque being applied by an engine. So you wouldn't have directional control, but the autorotation is also used in a tail rotor failure case. The vast majority of machines have a gearbox that links, so it's driven off of the main rotor head. So the main rotor head drives a big gear, which then goes through a shaft to the tail. So a lot of them do that. There's also belt configurations, and we also have things like direct drive, so putting a separate electric motor out on the tail. So in a main motor failure case, we still have full yaw control for navigating, but if in a tail rotor failure case, the end result is still to auto rotate to the best of our capability.
Okay, cool. Thank you.
Thank you very much. I know that Ferruccio just wanted to say a quick thanks. Ferruccio, do you want to?
I would like to say thanks to everybody, and especially a particular thanks for sponsoring me with the rangefinder, because I was using a 10-meter rangefinder with literally
Ferruccio, you cut out
didn't
a little
work.
bit.
So the
Cut out a
RGPilot team
little bit.
sponsored me a better sensor. Thank you.